Hey guys, this is Professor Janacek. I want to go over limits at infinity. Now, what makes this unique from, say, an infinite limit is that, in this case, limit at infinity means that the x value is going to infinity, or perhaps x is going to negative infinity. It's not that my limit necessarily equals infinity. It is true that this could be equal to infinity, or it could be equal to some number. But that's not necessarily the case for all of them. It's not necessarily always equal to infinity. The real thing with limits at infinity, again, is that the x value is approaching infinity or negative infinity. That's what makes these particular problems unique. So let's take a look at our first example. Let's take the limit as x approaches positive infinity of 2 plus 10 over x squared. So looking at this, I'm going to go ahead and kind of set up a table here. Let's say we'll choose some x values, and then we'll see what we get in our function. In this case, our function is 2 plus 10 over x squared. So let's just play around with some values. If we start with 1, put that in there, 2 plus 10 over 1 squared, we end up with 12. At 10, 2 plus 10 over 10 squared would give us 2 and 1/10. How about if x is 100? 2 plus 10 over 100 squared takes a little more computation, but let's see, we end up with 2 and 1/1000th. All right, what about if x is equal to 1,000? 2 over 10 plus 1,000 squared. Let's see, again, take your time with this computation if you need. That's 2 and 100,000 is what we end up with. Yep, that sounds good. All right, so you'll notice that as these x values are getting larger and larger, the function values, my y values if you will, those look like they're all getting pretty close to 2. Right? I suspect I'll just, if I keep going in this pattern, I'll just get things that are smaller and smaller bits behind the decimal, and so I end up with just a value of 2. So it turns out this limit is 2, and that's the basic idea behind a limit as x approaches infinity. Now, one thing to note with this, if you were to graph the function, if you were to say graph this function here, it would have a horizontal asymptote. So please make sure, what's going to help you with this is if you know your asymptotes. Both vertical and horizontal are very, very helpful, so make sure you know how to determine asymptotes. All right, continuing on, now let's take the limit as x approaches infinity of negative 2x cubed plus 3x squared minus 12. So in this case, there aren't any asymptotes if I were to graph this function, and I'm not going to do a table in this case. What I want to look at for this one is I want to compare what happens as x gets big, what happens to both x squared and x cubed. So as x is going to infinity, I'll notice that x squared is going to get big, right? Think about squaring numbers. Those get pretty big relatively quickly. I mean, but what happens to x cubed is that these get bigger. So the idea is that in this case, x cubed gets bigger kind of faster than x squared. So the x cubed term here gets bigger a little bit faster than the rest of it. Now let's talk about what's going on with these. If you look at the 12 here in the back, it's just going to stay 12. Regardless of how big x gets, 12 is just 12. And this 3x squared also gets big, definitely gets big. However, it's this negative 2x cubed, that's the one that gets bigger the fastest. So that's really what matters. Eventually, all of this other stuff won't matter. Yes, it's going to be some big stuff, especially in that x squared part, but eventually it's going to be tiny compared to x cubed. If my x value is big enough, then x cubed is huge, and x squared is relatively small. So eventually I just need to worry about what happens with that cube. So looking at that, what we end up with is we're going to have a negative, of course it's negative 2, but the 2 won't matter either because 2 times infinity is still infinity. 2 times a large number is still a large number. So don't worry about the 2, but I do need to concern myself with that negative. And I'm also looking at x approaching positive infinity. So that means I've got a positive raised to the third power. So a negative times a positive to the third power gives us a negative. So what we end up with is a negative, but it is still going in the infinite direction, so we end up with negative infinity for that one. Now for example 3, it's very similar. We're taking the limit as x approaches negative infinity this time of that same polynomial. So again, using that same logic, the 12 I don't need to consider because it stays as 12. And x cubed, although it gets big, it's nothing compared to the x cubed. X cubed is huge. X squared is big, but not as big as x cubed. So I can kind of ignore those for a bit and just worry about that. Again, multiplying by 2, a large number times 2 is still a large number, so I don't have to worry about the 2, but I do need to worry about those positives and negatives. In this case, I still have a negative out there, but now I'm also cubing a negative. So I've got a negative cubed times another negative. Well, if you think about all of those signs, in this case we actually end up with a positive. It's still getting really large, but now it's going in the positive direction. So make sure you understand what's getting large and how it's getting large. All right, so on to example 4. We're taking the limit as x approaches positive infinity of 3x plus 2 over x squared minus 1. Now, there are some techniques, there are various techniques for working with limits of rational expressions. You could, of course, graph this and take a look at the asymptotes. But there is a nice little technique that I would like you to become familiar with. And what I'm going to do is let me just rewrite this again so we can work with it. I'm going to take this exact same rational expression. But what I'm going to do is I'm going to take the term in the denominator that has the highest degree. In this case, that's x squared. So again, that x squared is going to be important to me. What I'm going to do is I'm going to multiply the numerator and denominator by the reciprocal of that term. And again, all I really need is the x portion of it. So I took that x squared and I'm going to multiply it, the reciprocal of that, by both the numerator and the denominator. Oops. So what that gives me, notice I still have to write the limit notation because I'm still taking the limit. And now I'm going to simply distribute out that 1 over x squared. So we end up with 3x over x squared plus 2 over x squared over x squared minus 1 over x squared. Let's go ahead and simplify that. Notice again, I still have to write that limit notation. I have not evaluated the limit, so that limit notation is still there. If we reduce, we end up with 3 over x plus 2 over x squared. In the denominator, we have 1 minus 1 over x squared. And remember that as x goes to infinity, 1 over x, so x is getting really large, 1 over x is getting really small. It goes to 0. And of course, if 1 over x goes to 0, that goes to 0. 1 over x squared, or 2 over x squared, goes to 0. And also, in the denominator, 1 over x squared, all of those go to 0. Again, make sure you understand that. As x gets really large, 1 over x gets really small. So now let's go ahead and evaluate the limit. So I don't have to write the limit notation. If I take the limit, again 3 over x, that goes to 0. 2 over x squared, that also goes to 0. 1, the limit as x goes to infinity of 1, well, that's just 1. There are no x's in that. And 1 over x squared, that also goes to 0. So we end up with 0 over 1, which is just 0. Now be careful, if it had been 0 over 0, there could have been a problem, but it's 0 over 1. We can work with that. And so there we go. We end up with just 0 here. All right, let's try this technique again with example number 5. We've got the limit as x goes to positive infinity of 40x to the 4th minus 4x squared minus 1 over 10x to the 4th minus 8x squared plus 1. So I'm going to just rewrite it again. Doesn't take but a second, and it's good to have all of your bits here where you can see them. And what we're going to do is we're going to take, again, the highest degree term in the denominator, the item with the largest exponent, just the x value. I don't need the coefficient. I don't need the 10. So just the x to the 4th. And we're going to multiply the numerator and the denominator by the reciprocal of that. Okay, now I'm going to go ahead and distribute. I'll go ahead and distribute and simplify at the same time. If you need to do it in 2 steps like we did in example 4, go right ahead. But if I distribute and simplify those, we get the limit as x goes to infinity of 40 minus 4 over x squared minus 1 over x to the 4th over, in the denominator we have 10 minus 8 over x squared plus 1 over x to the 4th. Again, take your time with that. If you need to distribute and then reduce like we did in the previous example, go right ahead. And so now let's see what happens as x goes to infinity, right? It's going to, x is getting really large. Anything that has an x in the denominator, all of those go to 0. Right? All of those get really, really small. So now that when we take the limit, I don't need to write the limit notation. The limit of 40 is just 40. The limit of 4 over x squared, that one's 0. The limit of 1 over x to the 4th, that's also 0. In the denominator, the limit of 10 is just 10. The limit of 8 over x squared, that one goes to 0. And 1 over x to the 4th also goes to 0. So we end up with 40 over 10, which reduces to simply 4. There we go. Now let's take a look at our last example here. We're going to take the limit as x goes to infinity of x cubed minus 2x plus 1 over 2x plus 4. We're going to use the same little technique that we just used. We're going to take that limit. Again, this is for rational expressions. So here's my rational expression. And now I'm going to take a look at the highest degree term in the denominator. I'm going to look just at the variable. That's all I need to concern myself with. In this case, that's just an x. So I'm going to multiply by 1 over x in both the numerator and the denominator. Now again, distribute this out and combine like term, distribute this out and then reduce. If you need to do that in 2 steps, feel free. I'll go ahead and do it in 1 step. I haven't taken the limit, so I need to write that limit notation. Very, very important. So we end up with x squared minus 2 plus 1 over 2 plus 4. Oh, sorry, hold on. In the numerator, that's not plus 1, that's plus 1 over x. And then in the denominator, we end with 4 over x. Now in this case, I notice that as x goes to 0, 1 over x goes to 0. I'm sorry, as x goes to infinity, 1 over x goes to 0, and 4 over x. Both of those get really small. So those go to 0. As x gets really large, 2 is just 2 in both the numerator and the denominator. So those kind of stay the same. X is getting really, really big, but those just stay as numbers. I may or may not need that. But what happens as x goes to infinity? What happens to x squared? That's the important one. Oh, let's see. This is really important. Remember, as x goes to infinity, x squared also goes to infinity. So it doesn't matter if we've got a 0 back here or a 2 back here. All of those don't matter. The only thing that really does matter is that I don't have infinity in the denominator, right? The denominator does not approach infinity. The denominator approaches 2. Now, I'm not going to say that this, notice I'm not going to write down that when we take this limit, we get infinity over 2. Because infinity is not a number, I can't really write it as a rational expression like that. So that's really just poor notation. The 2 is there, but at some point it doesn't matter, and infinity is, again, it's not really a number. So writing it as being divided by something or multiplied by something, or it just doesn't make sense. So I can say that this is equal to infinity, but I'm not going to say that it's equal to infinity over 2. And there we go. Enjoy.